In this video, we will derive some integral formulas using inverse trigonometric functions and their derivatives. These formulas will help us find integrals of few more types of functions. So first we have integral of 1 over square root of a square minus x squared. So we try to compare with one of the derivative formulas we are given here. It looks closest to this one, arc sine x. So our goal here will be to try to make this part look like 1 over 1 minus u squared so that we can apply this formula. One way to do that is to try to factor out a squared. This becomes dx over square root of a squared. Now, if we factor out a squared from the first term, we are left with just 1 minus from the second term, we will have x squared over a squared. And we have square root of a squared. So I can pull a out since square root of a squared is simply a. So we have 1 minus x squared by a squared. So this becomes of the form 1 minus u squared if I let u to be x over a. So we let u to be x over a. Now we want to write the whole integral in terms of x. Then we get du by dx equals 1 over a. And this implies dx equals a du. So now we are ready to write the integral in terms of u. So this becomes integral du over a square root of, sorry, dx is a du. I missed that a over here. 1 minus u squared. Looks like a's get canceled out from top and bottom. So we are left with integral of du over 1 minus u squared, but that is simply the formula we have over here. So therefore, this must be arc sine u plus constant, but u is x over a. So this becomes arc sine x over a plus constant. Now let's look at the next integral. So here we want to find the integral dx over a squared plus x squared. And looking at the derivatives we have over here, this matches best with this formula. Derivative of arc tangent of x equals 1 over 1 plus x squared. So we try to make the denominator look like 1 plus u squared. So for that, we can factor out a squared again. So it will look like a squared 1 plus x squared over a squared. This means if we let u to be x by a, then our denominator will look like 1 plus u squared. So we want to replace dx by an expression in terms of du. So we get du over dx equals 1 by a, which implies dx equals a du. Therefore, this expression becomes integral over dx is a du divided by, We have a squared factored out over here. So I'll just put that over there. 1 plus x squared by a squared is u. 1 plus u. So we have this 1 plus u squared. So x squared by a squared is u squared. We have 1 plus u squared. It looks like a and a squared will simplify to simply 1 over a. I'm going to put that in the front. So we have 1 over a du over 1 plus u squared. So looking at this formula, antiderivative of 1 plus u squared is simply arc tangent u and plus constant. So this becomes 1 by a arc tangent x over a plus constant. So this is the antiderivative for the second function, 1 over a squared plus x squared. Now let's look at the last one here. Integral of 1 by x square root of x squared minus a squared. Again, we can compare with these formulas for derivatives. With one, this function looks like, and we can see it's very close to this one over here. Using the same idea and using this formula for derivative, we can prove that this will come out to be 1 over a arc secant of absolute value of x over a plus constant. The proof for this one is very similar to what we did in the first two integrals, but we're going to skip that here. Next, we will look at some examples. So let's begin with the first integral we are given over here. So we are given integral dx over square root of 14 minus x squared. So looking at these three formulas for integrals, this one looks very close to the expression we are given. So we'll try to use this formula. Comparing the given expression with the formula, we see that a equals, basically a squared equals 14. So we will let a to be square root of 14. So therefore, I can say the integral 14 minus x squared equals arc sine x over square root of 14 plus constant. Quite straightforward, just applying this formula. Now let's look at the next one. So next we have integral of 1 over 2x times square root of x squared minus 2. Again, comparing with these three available formulas, this one looks very close to this third formula over here. So we'll try to use that formula. The first step, I can bring that 1/2 out. Then it will become more like the expression we have in the formula. X times square root of x squared minus 2 dx. And if we compare with this one, we can let a squared to be 2. So a is square root of 2. So this becomes 1/2 1 over a, which is square root of 2, arc secant, absolute value of x over square root of 2 plus constant. So that is the value of the second integral. Okay. Let's look at the next one, this one. Now again, comparing with these three formulas available, this one looks closest to the expression given. I can pull that 5 out and write this as 1 over x squared plus 9. And comparing with this expression, looks like we need to let a to be, well, a squared to be 9, that means a equals 3. Then this becomes 5 times 1 over a, which is 1 over 3, arc tan x over 3 plus constant. So we get 5 by 3 arc tangent x over 3 plus constant. Okay, this is the third integral. Now the last one on this page, we have a definite integral. So the integrand is the same, 5 over x squared plus 9, but we are evaluating it from square root of 3 to 3. So we can just use this antiderivative we obtained over here. So I'm going to keep that and do that over here. So this will simply come out to be 5 by 3 arc tangent x over 3 and evaluate x from square root of 3 to 3. So this becomes, I can pull that 5 by 3 out. So we are left with arc tangent 3 over 3 minus arc tangent square root 3 over 3. Let me erase this part here. So this becomes 5 by 3. Arc tangent 3 by 3 is arc tangent 1, which is pi by 4, minus arc tangent root 3 by 3 will be pi by 3, actually pi by 6. So we get pi by 4 minus pi by 6 over here. And I can simplify that. So pi by 4 is 3 pi by 12 and pi by 6 is 2 pi by 12. So we get pi by 12. So this comes out to be 5 pi by 12. So this is the value of this integral, the fourth one. Next, we will look at a few more examples. Okay, the first one on this page is integral of 9 over 14 plus 2 minus x squared. Again, we try to compare with one of these three formulas. It looks like it is closest in form to this one, the second one. So comparing with that one, we can let a to be square root of 14, so that this becomes a square. And we can let u to be 2 minus x, so that the denominator here becomes a squared plus u squared, because here we have a squared plus x squared. Okay, so now we want to express everything in terms of u. So for that, you want to find dx in terms of du. Since du by dx is -1, then dx is negative du. So now we are ready to express this integral in terms of u. So this becomes 9, well, negative 9 du on the top, divided by, so a is square root of 14. This becomes a squared plus u squared. So this is, I can always pull that -9 out. And it looks much cleaner now. So we have du over a squared plus u squared, which is exactly the expression we have in this formula. So dx over a squared plus x squared. So this will come out to be 1 by a arc tangent u over a plus constant. So now we are ready to put the values of a and u back. So that will give us -9 over square root of 14 times arc tangent u is 2 minus x divided by a is square root of 14 plus constant. So this is the integral. of 9 over 14 plus 2 minus x squared. We are done with the first one. Let's look at the second one now. So we compare with one of these formulas again. So this one looks more like the first one here, at least the denominator part, like this one. But we need to do some substitutions. Looks like a will be 1 because we have 1 squared here and we have a squared here. And then we have x to 4 here. So we have x squared here. We want to have 1 minus u squared so that it looks like 1a squared minus. So we want to have 1 squared minus u squared so that it looks like a squared minus x squared. So we can let u to be x squared so that this expression becomes u squared. Okay, now we are ready to do the integral. But before that, we want to express dx in terms of du. For that, we need to find du by dx, which is 2x. This implies dx equals du over 2x. Right, so now we are ready to express this integral in terms of u. So I'm going to leave that x as it is for now. Then dx is du over 2x divided by integral of 1 minus x to 4 would be u squared because u is x squared. So x to 4 is u squared. I can simplify this little bit further because this x and that x get cancelled out. I can pull that 1/2 out. So I'm left with du over 1 over u squared. This is exactly like what we have over here. So this becomes 1/2 arc sine u over a. Our a is simply 1 plus constant. So finally, I can put the expression for u back in terms of x. So arc sine u is x squared. So simply x squared plus constant. This is the second integral. Let's look at the third one. So again, we try to compare with one of these formulas, and it looks like it is closest to this one, at least the denominator. So comparing this denominator with a squared plus x squared, and we want to write this in the form a squared plus u squared. So looks like a will be 3 and u will be x minus 8. Now, since we want to write everything in terms of u, we can find du by dx. So this is 1, which implies dx equals du. So we are now ready to write this integral in terms of u. On the top, we have 5x. We can also express x in terms of u using this formula because x is simply u plus 8, adding 8 to both sides. So 5 times u plus 8 plus 6 divided by 9 plus u squared is what we have. And dx is simply du. Simplify this top part and see how it looks like. We have 5u plus 40 plus 6, which is 46, divided by 9 plus u squared du. Now I can write this as two integrals. Integral of 5u divided by 9 plus u squared du plus integral of 46 divided by 9 plus u squared du. Okay, so we are going to treat these two separately. Let me erase all of these so that we have some space. But I'm going to leave this part as it is. For the first one, I'm going to call the first integral, this one a, and this one b. Okay, so a equals, we have 5u over 9 plus u squared du. Now this looks like we can solve this by u substitution. So I'm going to use different letter. Let v equals 9 plus u squared. Then we have dv by du equals 2u, which implies du equals dv by 2u. So now I'm ready to express this integral in terms of v. So this becomes 5u over v, 5u over v, and du is dv over 2u. Okay. So we can cancel out u from top and bottom. Then we are left with 5 by 2 integral of 1 by v dv. So this is 5 by 2 natural log of absolute of v plus constant. And v is simply 9 plus u squared. So this will be 5 by 2 natural log of, and 9 plus u squared is always positive, so I don't need those absolute value signs, plus constant. So we get this one from A, and we need to do B also. So B equals, we have this integral, 46 divided by 9 plus u squared du. Then I can pull that 46 out and make it 1 over 9 plus u squared du. So with a equals 3, we get this integral to be 46 1 over 3 arc tangent u over 3 plus constant. So we got a and b. Now we just need to put them together because it's a plus b. I'm going to erase this part here. Therefore, this integral is simply 5 by 2 natural log of 9 plus u squared plus constant. We have plus constant in both of them. We'll just use one of them. Plus 46 by 3 arc tangent u by 3 plus constant. And finally, I can put the expression for u back. So this becomes natural log of 9 plus u squared is simply x minus 8 squared plus 46 by 3 arc tangent u is x minus 8 by 3 plus constant. Therefore, this is the antiderivative of this third function. Let's look at the next example now. Number 4. This is a definite integral. Now to find the antiderivative of this function, again, we try to compare with one of these given formulas, and it looks closest to the second one. So we will let a to be 1 because we want to write this as u squared plus a squared. So our a squared will be 1 squared, so a is 1. And our u squared is this whole thing. So we'll let u to be 2 sine x. Now we want to express the integral in terms of u. So we want to find dx in terms of du. But this implies du by dx equals 2 cosine x, since derivative of sine x is cosine x, which implies dx equals du over 2 cosine x. Dx equals du over 2 cosine x. So we have that. We also need to change the limits. When x equals 0, then u equals 2 sine of 0, which is 0. And when x equals pi by 2, then u equals 2 sine pi by 2, which is sine pi by 2 is 1. So therefore we have 2. So these will be the new limits. So therefore the integral becomes integral from 0 to 2 cosine x. I'm going to put 2 cosine x as it is, hoping that it will get cancelled out. And in the denominator, we have 2 sine square x, which will be, sorry, 4 sine square x, which will be simply u squared, because u is 2 sine x, plus 1. And we said dx is du over 2 cosine x. So therefore, this becomes 0 to 2. And it looks like cosine x goes away, and this 2 also goes away. So we are left with 1 over u squared plus 1 du. And it looks exactly like the expression we have here with a equals 1. So therefore, this integral becomes arc tangent u, and we evaluate this from 0 to 2. So this will be arc tangent 2 minus arc tangent 0. We know arc tangent 0 is 0. So therefore, this comes out to be arc tangent 2.